Assalamu alaikum wa rahmatullahi wa barakatuh. Let's continue with the energy equation, which we have started yesterday. Okay. Yeah. The energy equation. Uh, this is the Bernoulli equation. Okay. And this is the energy equation derived from the first law of thermodynamics. Okay. We will not go into so much detail into the derivation of the energy equation because it has to do a lot to do with thermodynamics, work, and energy. Okay. Uh, but the full derivation is in the text, which you can always check. Okay. So the energy equation is in a way different from the Bernoulli equation. Their derivations are different. Okay. Except that the terms are similar. Okay. The energy equation takes care of addition or subtraction of energy and also the head loss due to friction. Okay, if you remember, Bernoulli equation is applicable for non-viscous flow, and the energy equation is applicable for viscous flow, because when you have viscous flow, you have friction, and when you have friction, you have head loss as thermal energy. Okay, so that head loss as thermal energy is taken care of by the head loss term in the energy equation, which is missing in the Bernoulli equation. Then again, in the energy equation, it takes care of addition of energy by a pump. So this is the pump head, and subtraction of energy by a turbine. Okay, when you have a turbine. Okay, while for the Bernoulli equation, when you have a pump, a turbine, I mean, you cannot apply the Bernoulli equation because they don't take care of addition or subtraction of energy. Okay, they only take care of change of energy from one form to another, let's say from kinetic to flow or vice versa. Okay, and then again in the energy equation, the kinetic energy term is corrected, that is the velocity term, using the kinetic energy correction factor called alpha. Okay, alpha is called the kinetic energy correction factor because Coriolis, who is a scientist in the 18th century, realized that the actual kinetic energy the is greater than this value using the velocity, the average velocity obtained from a uniform distribution. Okay, this velocity is the average velocity obtained when the velocity profile is uniform. Okay, as we know in flow, the velocity profile more often than not is non-uniform. It's usually parabolic in most of the instances. So this alpha is taking care of, is like a correction factor for the kinetic energy to give us the actual kinetic energy of the flow at the point in question. Okay, and the alpha, the kinetic energy correction factor, is 1 for turbulent flow and 2 for laminar flow. Okay, because most of the flow we will encounter in pipe and what have you is turbulent flow. So that is why usually alpha is equal to 1. Okay, it's equal to 1 for turbulent flow and it's equal to 2 for laminar flow. Okay, so this is the full form of the energy equation. Okay, then depending on the problem at hand, if there is no pump, then the pump head will be 0. If there is no turbine, then the turbine head will be 0. And if head losses are negligible, then HL will be 0. But usually, head losses may not be negligible in most instances. Okay, but if you have a pump, then you insert the pump head. If you have a turbine, you insert the turbine head. Okay, and we are going to solve some problems related to this. Okay, so like I said, it's more or less the representation, or the energy equation was derived from the first law of thermodynamics, which states that during a process energy can not be created, or destroyed, but can change from one form to another. Okay, that is to say, during a process, okay, when you have energy input E1, energy output E2, so the change in energy is taken care of by E1 minus E2. Okay, so meaning the energy is conserved, just like we explained the mass conservation, where mass is conserved. So the same thing here, the change in energy, okay, which is delta E, is given by E1 minus E2. Okay, so energy is conserved in this case. That is the law of conservation of energy. Okay, so the energy of point 1 minus the energy of point 2 is equal to the change in energy. Okay, so this is the change in energy, which is delta E, and this is E1, okay, energy of point 1, and this is E2, the energy at point 2. Okay, and this is a more realistic representation of the Bernoulli equation when incorporating the energy, the change in energy, because there's always a change in energy more often than not, unless, of course, when the viscous forces are negligible. This we explained, we explained what thermal energy is, which refers to the energy content and the heat flow due to thermal energy. Okay, and we explained that power is rate of mass rate times GH. Okay, which is power, and head loss we explained is the conversion of the useful mechanical energy to waste thermal energy. So you can see how the change in energy is converted into waste thermal energy, because most of this, the head loss in particular and the change in the head, I mean, due to the pump head and the turbine head, is basically constituting the thermal energy. So Bernoulli equation involves only mechanical energy, while the energy equation involves mechanical and thermal energy. So this is the thermal energy component, okay, which is simply the heat, okay, which refers to the energy content within a system, which is responsible for temperature. Okay, and like I was explaining, this is the kinetic energy correction factor, okay, alpha. Okay, this is the actual, which is the ratio of the actual, the time rate of the actual kinetic energy over time rate of the average kinetic energy, assuming uniform velocity distribution, okay, which is V bar. Okay, so alpha is simply so you see, when you multiply this with the kinetic energy, okay, the average will cancel this and you will be left with the actual kinetic energy, okay, which, like I said, is more or less equal to 1 for turbulent flow. But we apply the alpha for the energy equation, not for the Bernoulli equation. And this is the summary. Like I said, alpha equal 1 for turbulent flow, and equal 1 for nozzles, equal 2 for fully developed laminar flow in a round pipe. Okay. And I already explained all these equations before. Now, this summarizes the process of applying the energy equation. Which one you select the energy equation when the problem involves a pump, a turbine, or head loss. Okay, more often than not, even if it doesn't involve a pump or turbine, you should always have a head loss. Okay, and you have to check to ensure that the assumptions are satisfied. And the assumptions are that you have steady flow and one inlet and outlet port, and constant density, that is, the fluid is incompressible, and negligible thermal energy terms, except for the head loss. Okay, because the head loss is the one containing, that's taking care of the thermal energy term. And then you select the control volume. Okay, you level the inlet port 1 section 1 and outlet section 2. And then by conventions, engineers do not sketch control volume when applying the energy equation. In the analysis, you write the general form of the equation and conduct term by term analysis. Okay, and you simplify the general equation to the reduced equation. And you have to ensure the units are homogeneous. Okay, head in via flow and pump. Okay, so let's take some example here to demonstrate the application of the energy equation. So applying the energy equation to predict the speed of water in a pipe connected to a reservoir. Okay. Here you have the problem statement, which states that you have a horizontal pipe which carries cooling water at 10 degrees Celsius for a thermal power plant. The head loss in the pipe is given by this. Okay. We are going to see later in chapter 10 that this is called Darcy-Weisbach equation, which is the Darcy-Weisbach equation, which is the equation for the head loss. It can be used for head loss in pipe and also the head loss in open channel as well. Yeah, it's also used for open channel. Okay, so and this is called the friction factor, this constant 0.02. We are going to analyze this later in chapter 10. Okay, so this is the head loss in the pipe. So pipe is connected, the distance, the length of the pipe 2 kilometers, the elevation here is 20, here is 100, and the mean velocity, V is the mean velocity in the pipe, and D is the diameter. If the pipe diameter is 20 centimeter and the rate of flow is 0.06, what is the pressure in the pipe at L equal 2000? So what is the pressure at this point? Okay, we know the pressure is going to be decreasing, okay, from this point to that point. Okay, so what is the pressure here? Okay, so in this case, water flows, okay, we have the height, the diameter, the head loss in the pipe, we have the flow rate. Okay, so we can find the velocity. So the assumption here, because normally have turbulent flow alpha equal 1, okay, and this is the specific weight of water. So here we generate the ideas and make a plan. And here we select the energy equation because the situation involves water flowing through a pipe, and the energy equation contains the goal, P2. And also, it has head loss. So we cannot use the Bernoulli equation here. And we want to know the pressure. So we write the energy equation and solve for P2. Okay. Here, P1, we take it to be at this point. Okay, this is P1, which is the pressure is atmospheric, which is 0. Okay, and P2 is what we want to find. Okay, P2 is what we want to find. Because there is no pump, so the pump head is 0. There is no turbine, the turbine head is also 0. And at point 1, the velocity is very small. Okay, so the velocity almost 0. Okay, and Z1 is 100 and Z2 is 20. And we can find V2, okay, because we have the flow rate. Okay, we have the flow rate through the pipe, and we can find the area pi d squared over 4. Okay, so this is V2. Okay, and we can also find the head loss using the head loss formula, which I called Darcy-Weisbach equation. Okay, called DW, Darcy-Weisbach. Darcy-Weisbach. These are the names of the scientists that worked to formulate the equation, okay, which indicates that the head loss is proportional to what is simply like kv squared. Okay, it's proportional to the velocity squared. So as the velocity increases, the head loss increases. Okay, as the velocity increases, the head loss increases, and also as the length of the pipe increases, the head loss increases. And based on this, as the diameter decreases, the head loss increases. Meaning for larger diameter, you have less head loss. Okay, for larger diameter. And for smaller diameter, the head loss is higher. And that is because you will have, the flow will be more or less viscous. It will be affected by friction, by shear stress. Okay, the shear force will be high. So here we substitute to find the head loss. And then from there, we substitute back to get P2 because all the terms are known. Okay, so we substitute back to make P2 the subject of the formula. And this is P2, okay, which is gauge, okay, kilopascal. So the key idea here, we select the Bernoulli equation is if viscous effects can be neglected, and select the energy equation if viscous effects are significant. And how do you know whether they're significant? If you have the head loss, okay? From the question, we were given the head loss, okay? So from there, we should know. We should know that we have to apply the energy equation. Now, the power equation, okay? Power is simply the rate of doing work or the rate at which energy is transferred, okay? So how can the pump head and the turbine head be useful to us? They will be useful to us in calculating the power generated by, needed by a pump, or the power produced by a turbine, because turbine produces power, okay? And then pump extracts power, it utilizes power, okay? So calculating the power of pumps and turbines, we simply use this formula, from uh, uh, gamma Q. You remember before we wrote that power is m dot gh, okay? And what is m dot? Is the rate of mass transfer, okay? Gh. And then what is mass? Density times volume, okay? Gh. So volume over time. And what is volume over time? Volume over time is Q. So rho Q GH. And what is rho G? That is gamma. Rho and G will give us gamma. So gamma QH. Okay. So that is how this equation was arrived at from the definition that power is the rate of doing work. Okay. MGH over T. So gamma QH. And for angular, you know, uh, for angular power, you have torque times the angular speed. Okay. And H here is the head of pump or turbine. This H is the head of the pump or turbine, which can be obtained from the energy equation as HP or HT. So the summary of the power equation here, we have power equal, force times velocity. Okay, this I explained in our previous class, how we got power to be force times velocity. Okay, because power is simply force times distance over time. Okay, distance over time is velocity, so force times velocity. Okay, so and this is most applicable for airplane, submarine, or a car. Okay, and for rotational motion, you have power equal T omega. Okay, and the power supplied from a pump to a flowing fluid and power supplied from a flowing fluid to a turbine, we use gamma QH. We'll take some examples to demonstrate the application of these power equations. This problem says applying the energy equation to calculate the power required by a pump. Okay, so power required by a pump, which means we need to get the pump head and then substitute in the power equation to get the power required by the pump. And to get the pump head, we need the Bernoulli equation. So like this is an overview of the problem. Then the remaining is to plug in the numbers and then do the calculations, the mathematics, okay? Now here it says you have a pipe which is 50 centimeter in diameter and carries water at a rate of 0.5 cubic meter per second, okay? And a pump in the pipe is used to move the water from an elevation of 30 to 40, okay? So this is the pump. It's raising the water from the elevation of 30 to 40. Okay, so it is increasing the pressure. Okay, it has to increase the pressure in the flowing fluid. Okay, the pressure at section 1 is 70 kilopascal gauge. Okay, so this section 70 kilopascal gauge, and the pressure at section 2 is 350 kilopascal gauge. Okay, what power in kilowatts and in horsepower must be supplied to the flow by the pump? Okay, so what power must be supplied to the flow by the pump? So the power needed by the pump to increase this pressure from 70 to 350. Okay, and assume the head loss to be 3 meters of water and alpha equal alpha 1 equal alpha 2 equal 1. So we have a turbulent flow. Okay, so the head loss is already provided as 3 meters of water. Now, here we need the power in watts and in horsepower. And because the problem involves water being pumped through a system, it is an energy equation problem because we have a pump, okay, and head loss. However, the goal is to find the power. Okay, so we write the equation at sections 1 and 2, okay, which is the energy equation. This is, we write the equation in full and then we do the term by term analysis. Okay, we don't have any turbine, so the turbine head 0. We need the pump head. This is what we want to find. P1 is already given, P2 is already given. We can find V1 using the flow rate over the area. We can find V2 using the flow rate over the area. Okay, so all this we can find. And because V1 equals V2, the velocity is just the same. Okay, because if you look at the flow section, the section of the pipe is the same, so they cancel out. You will have the same velocity because the velocity is Q over A. Q is the same, the flow rate is the same, the area is the same, so the velocity is also the same. So the velocity head cancels out. And then this reduces to this, okay? And then we can make HP the subject of the formula and substitute the values to get HP, okay? So HP is simply 41.5 meters, okay, 41.5 meters. You see, this is due to the pressure difference, okay? This is the pressure difference for the 2 points, and this is the elevation difference, okay? And this is the head loss, okay? This is the head loss. So the physics here is that the head provided by the pump, which is 41.5, is balanced by the increase in the head, okay, which is 28.5, plus the increase in elevation, plus the head loss, because the pump is taking care of the head loss, okay? It is taking care of the head loss. And the power equation, yeah, we have Q, we have HP, we have gamma. This is the power in kilowatt, which we can convert to horsepower. 1 horsepower is 746 watts, okay? 746 watts, okay? So, and when pumps are usually rated in horsepower, which is not the SI unit of power, okay? You can buy a pump, 1 horsepower, 2 horsepower, 3, like that. So this is 273 horsepower. So it is really a high capacity pump. And then the discussion here we have, the calculated power represents the work over time being done by the pump impeller on the water. And the electrical power supply to the pump will need to be larger. Okay, will need to be larger than 204 kilowatts, because of energy losses in the electrical motor and because the pump itself does not work 100% efficient. It does not produce this 204. Okay, so you need to supply more if you need this output because of the efficiency. Okay, both of these factors can be accounted for using pump efficiency and motor efficiency respectively. Okay, because the pump has a motor, and we will explain about the efficiency in the next. Yeah, explain about the efficiency here. Now, can pumps and turbines deliver 100% power? Let me go back and explain something here. You see here, what power in kilowatt and in horsepower must be supplied to the flow. Okay, so we found that the power to be supplied to the flow is 204 kilowatt. This is the power to be output. This is the power output from the pump. Okay, 204. Then what about the power input into the pump? Is it 204 kilowatt? No, because when you supply 204, exactly 204, the output will not be 204. It will reduce because of the efficiency. There will be energy losses within the pipings, within the pump system. So it cannot deliver exactly the input power. So it has to be less than this. So to maintain, if we want 204, we have to supply higher. Let's say 250, depending on the pump efficiency. Maybe if you supply 250, then the pump can produce 204. Okay. And the difference, the output over the input, it gives the efficiency of the pump. Okay. How efficient is the pump at delivering, at producing an output that is almost the same as the input. Okay. And this is the efficiency. We'll talk about the mechanical efficiency. And can pumps and turbines deliver 100% power? No, they cannot, because there are losses, frictional and thermal losses, frictional losses within the pump and the turbines. And for that, they cannot deliver all the power input that they received. Okay. So pumps and turbines lose. Oh, no. Yeah, it should be loss. Let me. This is like 23. Okay. So here it should be lose with E. Okay, I'll correct it. Pumps and turbines lose some of their efficiency due to some factors such as friction and leakage. Okay. And energy losses are accounted for by using the efficiency. This is eta. Okay, it's pronounced eta, is a Greek letter, which is power output from a machine or system over power input to a machine or system. So output over input. So usually the input is greater than the output. So this ratio is usually less than 1. Okay, or if you want to make it in percentage, less than 100%. That is when you multiply this by 100%. Okay, so the efficiency of a machine is usually less than 1. The closer it is to 1, the better. Because if you have a machine that is 70% efficient, whose efficiency is 0.7, and one whose efficiency is 0.9, this is better, because it means this one can work at 90% efficiency, meaning it can convert the input power. 90% of the input power can be converted to output, while this one converts only 70% of the input power, meaning the loss is here, you have 30%. The loss is here, you have 1%, 10%. So here there are less losses than in this case. Okay, so the efficiency, the closer it is to 1 or to 100%, the better. Okay. Now let's take some example here. You have, suppose an electric motor. This is an electric motor. Okay. Like a generator. Okay. Is drawing 1000 watt of electrical power from a wall circuit, as shown in this figure. The motor provides 750 joules per second. That is also power. Okay. Watt and joule per second are the same thing. Okay. So the input here is 1000 watt, and the motor, the output from the motor is 750 joule per second of power to its output shaft. So this is connected to a pump. Okay, this power drives pump. Okay, the shaft drives pump, and the pump supplies 450 joules per second to fluid. You can see the original input into the motor 1000 watts, and the motor produces only 750. You see, it cannot produce 1000 because of the losses. So the output from the motor is 750 to a shaft which turns a pump, and then the pump produces 450. It receives 750 but produces only 450. So how can we find the overall efficiency here? The overall efficiency, or the combined efficiency of the system, it will be the final output over the initial input. Okay, which is going to be 450 over 1000. Okay, so which is 0.45 or 45% efficient. Okay, this is the combined efficiency, which is combined, because this is the efficiency of the motor and the shaft. For the motor, the efficiency of the motor is what? 750 over 1000. that is output from the motor over the input into the motor, which is 75%. And the efficiency of the pump is 450 over 750. Okay, 450 over 750. Okay, 450 over 750, which is what? Which is 60%. Okay, which is 60% efficient. But the combined efficiency now is 45%. And this 45% can be obtained by multiplying the efficiency of the motor and that of the shaft. So this is simply saying is equal to 75% times 60%. Okay, when you multiply the efficiency of the motor and the shaft, you will get the efficiency of the pump. Okay, or when you consider the initial input over the final output, it will also give you the same answer. Okay, and this is exactly what we have. Okay, from electrical grid, it takes 1000 watt or joule per second into the electric motor, and the electric motor produces 750 into the pump, and the pump produces 450 to the flowing fluid. Okay, so the efficiency of the motor is 750 over 1000, 75%. The efficiency of the pump is 450 over 750, which is 60%, and the combined efficiency is the final output over the initial input, which is 45%. Okay, and this, like I said, is the combined efficiency is simply the efficiency of the pump times the efficiency of the motor. Okay, which is simply 70, that of the pump 60% times 75%. When you multiply this out, you will get 45%. Okay, I hope it is clear. Now this is the summary of the efficiency equation. When you have a pump, is the efficiency of the pump times the power received by the shaft, because a pump has a shaft which is rotating. Okay, so the power that is supplied to the pump shaft. Okay, and the pump power is m dot gh, or this. Okay, and for turbine, the power of the shaft is equal to the efficiency of the turbine times the power received by the turbine. Okay, so let's take an example here and look at the demonstrate the application of the efficiency equation. Okay, so here we'll apply it to applying the energy equation to predict the power produced by a turbine. Okay, so here it says at the maximum rate of power generation. Okay, a small hydroelectric power plant takes a discharge. This is a turbine. Okay, you can see this is called a penstock, which is large diameter pipe conveying water from higher elevation. You can see the elevation here is 0, this is 61, which is very high. Okay, and this is a dam. Okay, and this is a reservoir, so the water is transferred, so it has a lot of energy to turn the turbine, and the turbine is connected to electric motor which produces electricity. Okay, so here you have the flow rate 14.1 meter per second through an elevation of 61 meters, and the head loss through the intakes, penstock, and the outlet works is 1.5 meter. So this is the total head loss, combined total head loss, and the combined efficiency of the turbine and electrical generator is 87%. Okay, so the efficiency is 87%. What is the rate of power generation? So to get the rate of power generation, we need to get the head supplied by the turbine. Okay, using the energy equation. Okay, so this is the energy equation. We don't have a pump, so this is 0, but we have a turbine now, and the head loss has been provided, was provided to 1.5 meters. Okay, and here you see here, this is our point 1 and this is point 2. Okay, point 1 and point 2. So this, the velocities are all 0. Okay, so the velocity terms cancel. Okay, and the pressure is atmospheric, so also they cancel out, but we have elevation difference. Okay, so now we can find the head loss due to the head of the turbine. Okay, using the difference in elevation and the head loss. Okay, so here it means that the head supplied to the turbine, which is 59.5, is equal to the net elevation change of the dam minus the head loss. Okay, so the head supplied to the turbine is the difference in elevation, okay, which is 61, minus the head loss. Okay, minus the head loss, because the head loss is wasted. Okay, it's wasted thermal energy within the pipeline. Okay, minus the head loss. And the power input to the turbine is calculated using the power equation. We have the flow rate, we have the head of the turbine, which is in megawatt. Mega, that's 10 to the power 6. Okay, and then to find the we now use the efficiency equation to get this is the power input to the turbine. What about the power output? Because here it says what is the rate of power generation, okay, which is the power output from the turbine, not the input. The turbine receives 8.23 megawatt from the flowing fluid, but can it produce this amount? No, it has an efficiency, a combined efficiency of 87%, which is the efficiency of the turbine and the electrical generator. So it can only produce 87% of the power it receives. So it can only produce 87% of 8.23. So the power output from the generator is equal to the efficiency times the power input, because efficiency, eta, okay, is the power output over the power input. Okay, so power output is simply the efficiency times the power input, and the power input is the power received from the flowing fluid, which is 8.23. Okay, so this is now the power output, 7.16 megawatt. Okay, and here the maximum power that can be generated is a function of the elevation head and the flow rate. Okay, you can see, because P is what, gamma QHT. Okay, so it's a function of uh, um, the turbine head, okay, which is a function of the elevation head, okay, and the flow rate. Okay. At any point in time, if you have any question, please ask. Okay. You know, this online thing, I'm not seeing you, and sometimes when I ask question, no response. So I have to be talking and talking, and then whenever you have question, I have already enabled your mic, so just stop me and then ask your question at any point in time. Now applying the energy and momentum equations to find force on a pipe contraction. You remember in the previous chapter, which is chapter 6, we looked at the momentum equation, where we apply the momentum equation in finding the force needed to hold a pipe bend. Okay, so here we want to apply the same, the energy and momentum equation to find the force on a pipe contraction. Okay, when there is contraction and expansion, you have forces associated with that. So what is the force needed to hold the pipe, okay, at a pipe contraction? So here you have a pipe whose diameter is 30 centimeter and carries water, and the pressure is 250 kilopascal at a rate of 0.707 meter cube per second. The pipe contracts to a diameter of 20 centimeters. So the diameter here is 30, and then at point 2 is 20. The head loss through the pipe contraction is 0.1 V2 squared over 2G. There's always head loss due to contraction or expansion, and these are called minor losses. You have major losses, which are due to friction, okay, due to shear effect, okay, due to viscous forces, okay, which is the head loss due to friction, HF. This is major loss, is the major loss contributing to losses in pipelines and flows, okay, and you have minor losses, HM, okay, when you have contraction, when you have expansion, when you have a valve, a pump, you know, all these, when you have a bend, you all have losses, but they are minor compared to the head loss due to friction. And more often than not, we neglect them. Okay, we'll also discuss probably about this in chapter 10. Okay, so this is a minor loss, and the general form of the minor loss is a coefficient, then this times the velocity is proportional to the velocity head. Okay, so this is the coefficient of the minor loss, okay, which in this case is 0.1. So what horizontal force is required to hold the transition in place? So what horizontal force is required? You can put the direction of the force this way or that way, okay? Here is written as this way, so you can assume any direction. And then you apply the energy equation, you know, and the momentum equation to find the force, okay? Assumed kinetic energy correction factor is 1 at both inlet and the exit. Okay, so here we have 2 points, 1 and 2. Okay, the diameter, the pressure here P1 is known, but we don't know the pressure at point 2. Okay, we don't know the pressure at point 2. And definitely because of the fact that the velocity will increase, the pressure is going to drop at point 2. It is expected to decrease because the velocity increases. Okay, so to find P2, we need to apply the energy equation. And then we apply the momentum equation to find the force, Fx. Okay, so when we, let's sketch, okay, the momentum equation, we sketch the force diagram and momentum diagram. This is the force diagram where we show the pressure force acting, which is compressive, P1A1, P2A2. And then we have Fx. And then we have the momentum equation. This is the inlet and this is the outlet, okay? The initial momentum and this is the final momentum. And when we write X direct the momentum equation, when we sum all the forces, this is positive, negative, positive, positive. Okay, so it's equal to the rate of change of momentum, the sum of all the external forces, which is in this case the pressure force and the force needed to hold the contraction in place. Okay, which is this one. So the sum of all the forces, you know, just applying Newton's second law of motion, summation Fx, F is equal to the rate of change of momentum. Okay, is equal to the rate of change of momentum, okay, which is m dot v. Okay, and here v1 is different from v2. Of course, we should know that because of the contraction, v2 will be greater, is greater than v1 because of the contraction. Okay, so the flow will be accelerated, and if it is accelerated according to Euler's law, which is minus del P is equal to rho A. If it is accelerated, then the pressure gradient upstream will be higher, okay? Because this is now the direction of acceleration, okay? So the pressure gradient is higher here. So in this case, based on this, also I'm based on the piezometric equation Pz plus the velocity head, based on the Bernoulli equation equal constant, because the velocity increases, so the pressure has to decrease. Okay, so all these are indicating that P2 will be less than P1. Okay, P2 will be less than P1. Don't forget, if it is accelerating, then the direction of acceleration is this. If it is decelerating along the flow direction, then the acceleration direction will be in the opposite. This is for deceleration. This we did in the Euler's equation, I think chapter 4, okay? And we are going to take a quiz on the Euler's equation today at the end of the class. So we should expect P2 to be less than P1, okay? And to find P2 and substitute here, because we need P2 here to find Fx, okay? So we need to use the energy equation, okay? And when using the energy equation here, this is now P2, okay? We don't have any turbine or pump, so they are all equal to 0. And we can find V1 and V2, okay? Because we have Q, the same Q because of continuity, but the areas are different. So you can see that V1 is 10 and V2 is 22.5. So, you know, even before you do it, you should know that V2 should be greater than V1, okay? It should be greater than V1. Now we can find the head loss using V2, which is 2.58. And then we now substitute to find P2. We substitute in the energy equation here to find P2, which is 21.6. What is P1? P1 is 250. You can see that P2 is less than P1. Okay. So even without finding it, you should know that when you get, let's say 300, you know definitely you are wrong because it should be less. Okay. It has to be less than the pressure. Okay. It has to be less than P1 because of the increase in velocity and because of the acceleration of the fluid particles. Okay. So once we got P2, we can simply go back here and substitute to get Fx. Okay. Because all these are known. Okay, V2, V1, P1, P1, P2, they are all known. So we just substitute to get Fx, which is minus 8.13 kilonewton. And minus, it means it is acting to the left because we assume it is acting to the right. So it is actually acting this way. Simple. Because the magnitude of a vector quantity is always a positive number. Okay, it's always positive. So when you have minus, it's just about the direction. Okay. So I hope this is clear. And now uh, I have started contrasting the Bernoulli and energy equation at the beginning, okay? But these are some things to also help you out. Okay, the Bernoulli equation and energy equation are derived in different ways. Okay, we know the Bernoulli equation was derived from the Newton's second law. Okay, and then integrating the resulting equation along a streamline by applying, putting the acceleration of the particle and then integrating to find the Bernoulli equation. While the energy equation was derived from the first law of thermodynamics and then using the Reynolds transport theorem. Okay, so even the derivations are different. And then consequently, the Bernoulli equation involves only mechanical energy. Okay, this I explained. Whereas the energy equation involves both mechanical and thermal energy. The thermal energy is in form of the head loss. Okay, the head loss is the term constituting the thermal energy, which is zero in the case of Bernoulli equation. Okay. So the two equations have different assumptions, and they differ mainly in the viscous effects. In Bernoulli equation, the viscous effects are negligible. Hence, it applies to the implicit region, and the energy equation it takes care of the viscous effect, so it applies to the viscous flow region. Okay, because in the viscous flow region, that is when you have the head loss due to friction. Okay. And also, the Bernoulli equation does not take care of any additional energy being added through a pump or extracted through a turbine. Okay, so when you have a pump, you cannot apply the Bernoulli equation. When you have a turbine, you cannot apply the Bernoulli equation. But the energy equation takes care of additional energy being added or subtracted from the system. Okay, which is the energy equation. And under special circumstances, the energy equation can be reduced to Bernoulli equation. What are these special circumstances? When the head loss is zero and when the pump head and the turbine head are all zero. Okay? When they are all zero, so they will reduce, the energy equation will be reduced to the Bernoulli equation. And the grand summary is that the energy equation is not the Bernoulli equation. However, both equations can be related to the law of conservation of energy. Okay, because the Bernoulli equation is simply the law of conservation of mechanical energy. Okay, while the energy equation is the general conservation of energy, not only mechanical, because thermal energy is not mechanical energy. Okay, so it involves thermal energy, it involves a non-mechanical energy in the energy equation. And that is why you have similar terms appearing in each of the equations. So this is very important, for conceptual understanding of the two equations. So now we'll move on to the energy heads and the explanation of the energy grade line and the hydraulic grade line. So we'll take some few minutes break and I'll come back. We'll look at the how do we sketch the energy grade line and the hydraulic grade line. Okay. Yes, we are back from the break. Let's continue. You can see that I have just 13 students present, so 2 are absent. So the energy, still on the energy equation, because this is related to the energy equation. Let me see, did I enable the mic? Okay, yeah, the mic is enabled. All right. So sometimes it's helpful to represent the energy and heads using visual approach. Okay. So here we will have the energy grid line and the hydraulic grid line, which we have also shown this. We have shown these two lines using the Bernoulli equation. But for the Bernoulli equation, we assume they are constant. When you have a pipe flow, okay, the energy equation, this is the energy grid line EGL. This is the hydraulic grid line HGL. The hydraulic grid line is simply the height to which water will rise when you have a piezometer, okay, indicating the piezometric height. And the energy gradient is simply the height to which water will rise when you have a pitot tube, okay, because it gives the velocity head. This is the velocity head, okay. So for the Bernoulli equation, because it's an ideal case, okay, no head loss, so they are parallel to the pipe section, and the two are parallel, and the difference between the energy gradient and the hydraulic gradient is the velocity head, okay. So of course, if the velocity is constant, the difference will remain the same unless there is maybe contraction or expansion. When there is contraction, the velocity increases. Hence, once it increases, then the pressure drops. Okay, so there will be difference. Okay, so it will like drop. Okay, and that means the velocity head increases because there's increase in velocity. Okay, so this will expatiate more, but here we'll take care also of the losses, the head losses as water is flowing, because this is the ideal case of Bernoulli equation. In real sense, they are not parallel as it is. I mean, they are not like this. We have to take care of the head losses. Okay, so we'll itemize the steps, all that it takes in drawing the hydraulic grid line and the energy grid line. So the energy grid line is simply a line that indicates the total head at each location in the system. And recall that the total head characterizes the energy as discussed, okay, in the previous lecture, okay. The total head excluding the losses, okay. So the energy grid line is the total head, which is the velocity head plus pressure head plus elevation head, okay. So this plus that without the losses, okay. And the hydraulic grade line is simply a line that indicates the piezometric head, okay, at each location, okay. And the piezometric head is sum of the pressure head and the elevation head, okay. So together gives the hydraulic grade line, okay. And because the hydraulic grade line gives piezometric head, the hydraulic grade line will be coincident with the liquid surface in a piezometer, okay, while the energy grade line will be coincident with a liquid surface in a pitot tube, because the pitot or stagnation tube, because the pitot tube measures the velocity head, while the piezometer does not measure the velocity head. It measures only the piezometric head, okay, or specifically it indicates the pressure head in the pipeline, okay. It indicates the pressure head in the pipeline, okay. So this is now indicating the pressure head, okay. And when you look at the elevation, so it gives the piezometric head, okay. But it means that ideally, when you have this tank at this point, okay, the pressure head according to the Bernoulli equation should be the same. When you have a piezometer here, the pressure head should be the same, okay, according to the Bernoulli equation, although it will slightly drop because of the head, the velocity head. So it will be something like this and then like this, okay. So so this will be Yeah, yeah, the velocity. Yeah, yeah. So to take care of the velocity head, okay, so here will be the pressure head, okay, and the total because of the velocity head, because as it is flowing, it has velocity head, okay. So the total should add up to the height in this case. This is according to the Bernoulli equation. But in the real case, at this point, the pressure is low, is lower. You can see it will be decreasing the pressure head, okay? It will be decreasing because of the head loss due to friction, okay? As it is flowing, the velocity, the pressure head is decreasing, and then the energy grade line is also decreasing. You can see that it's going down because of the velocity head, okay? And the difference between the energy grade line and the point where it is supposed to be is accounted for by the head loss. Okay, the head loss is the one pushing them down instead of being horizontal as predicted by the Bernoulli equation. Okay, so the pressure head is losing pressure, you know, as it is flowing, it's losing pressure. The pressure head is reducing, is reducing. When it is coming out here, the pressure is atmospheric. Okay, so it is zero, as it is zero here. When you put a piezometer here, it will not rise to this point. Okay, this is the level it will rise in this case. In this case, this is the level to which water will rise. So you can see the pressure head is continuously decreasing with the flow, in the flow direction. And when it decreases, the energy grade line slope, because the velocity is assumed to be constant in this case, so the difference between the energy grade line and the hydraulic grade line is constant, okay, because the velocity here is the same. But if the velocity changes, the difference will either increase or decrease depending on whether the velocity has increased or decreased, okay. So how do we draw this? Okay, we have some drawing tips here in which, you know, we'll take it one by one. In a lake or reservoir like this one, okay, in which water is static, okay, the HGL and EGL would coincide with the liquid surface. So at this point, when it is static, it will coincide. O will indicate piezometric head. And why? Why will they coincide? Because the velocity is zero, okay. So hence the energy grade line will coincide with the and the static or gauge pressure is zero also, so it will just coincide with the liquid surface here, the energy grade line and the hydraulic grade line, because the pressure is zero and the velocity is zero. So EGL will be zero and hydraulic grade line will coincide with the, if pressure is zero, okay, if the pressure is zero at this point, okay, then you have only the elevation head, okay, you have only the elevation head at this point, okay, at the top, while at this point the energy grade line, the total head is zero because of the fact that the energy grade line is the sum of the hydraulic grade line plus the velocity head. So the velocity head is zero, okay, and energy grade line is equal to Z, which is up to the top of this, okay. So energy grade line is equal to hydraulic grade line in this case, and is equal to the elevation, okay, the elevation of the water surface, okay. So this is at this point, okay, which is exactly this point, okay, before the water, you know, gets into the pipe. Now, a pump causes an abrupt rise in the EGL and HGL by adding energy to it. We say that pumps, it has a pump head, isn't it? Which it imparts on the water. So if this is the pressure head, when it goes through the pump, it gets a boost, abrupt rise in EGL equal to HP. Okay, so there is rise in the energy grade line, which is equal to the hydraulic head, which is equal to the head of the pump. Okay, so the hydraulic head and the HGL will both rise by an equal amount equal to the pump head. Okay, so at this point, when you have a pump, then there is rise in the pressure head. You can see from here to here, okay? And then it continues to flow, and because it will be losing head, that's why it is sloping down, okay? And the slope of the energy grade line, we usually call it SF, friction slope, and the slope of the hydraulic grade line, we call it SW, which is because normally we have the water slope, okay? And then the slope is normally given as the head loss, okay, over the length of the pipe, okay? As the head loss occurring per unit length of the pipe, okay? This we will discuss also probably in chapter 10. So this is the rise, okay? And then again, when you have a turbine, there will be drop in the EGL and HGL because a turbine removes energy from the flow, okay? So here, when you have a turbine, this is the EGL and HGL. Here you have a turbine, it drops the energy level, the pressure head, because the turbine extracts the energy, utilizes the energy from the moving fluid, okay? So this is the head due to the turbine, okay? And then this is it. So also a component that generates a significant frictional effect, such as a valve, causes a sudden drop in both EGL and HGL at that location. Okay, when you have a valve, also you will have a drop in the energy level. Okay, when you have a valve, when you have contraction, or when the pipe contracts, okay, because there is energy loss also, so it will be reduced. But when you have a valve, there will be sudden reduction in the energy in the EGL and HGL. Okay, and then for steady flow in a pipe of constant diameter and wall roughness, the slope delta HL over L of the EGL and the HGL will be constant. Okay, so this slope, the head loss per unit length of the pipe, will be constant when you have constant diameter and wall roughness. So the slope will be constant. Okay, so if it will be constant, it means they will be parallel. So this will be parallel to this one. So this is because the velocity is assumed to be the same. Okay, here the velocity of flow is the same. That is why we say for steady flow. Okay, meaning the velocity at a given section does not change. Okay, the velocity at a given section does not change. So it will be more or less parallel. Okay, and the difference between EGL and HGL will be given by the velocity head. And tip number 5 is locate the HGL below the EGL by a distance of the velocity head. This we know. Okay, HGL is always below the EGL by a distance of the velocity head. Okay, these two curves approach each other as the velocity decreases. Okay, as the velocity decreases, they approach each other and they diverge as the velocity increases. Okay, okay, let's assume, okay, we will indicate this in another diagram. Okay, they come closer together, meaning the distance between EGL and HGL reduces if the velocity reduces, and the distance between HGL and EGL and HGL increases if the velocity increases. Okay, now in an idealized Bernoulli type, okay, the EGL is horizontal and its height remains constant when you have idealized Bernoulli equation, because there is no head loss in this case. So EGL is horizontal, you can see that, okay, and HGL will vary depending on the velocity, because here you can see the velocity is if this is V1, V2, V3. So here V2 is greater than V1. So that is why, there is sag, this increases the distance between EGL and HGL increase because of the increase in velocity. And then V2 is greater than V3. Okay, so V3 is less than V2. And that is why here you can see the difference between EGL and HGL decreases because the velocity has decreased. So also the distance. Okay. But this is for idealized Bernoulli type flow, okay, which is horizontal. In the real flow, you don't have it to be horizontal. The energy grid line is not horizontal. What is horizontal is the total. This is the energy grid line is called the total head. Okay, so the total energy is what is horizontal. Like in this case, the total energy now will be here from the top. And the total energy now is the sum of the elevation head, the pressure, the velocity head, and the head loss. So this is the total energy. So it's one that will always remain horizontal, okay, because it is taking care of the losses. So for open channel flow, the hydraulic grade line coincides with the free surface of the liquid, and the energy grade line is a distance. So when you have open channel flow, let's say in streams and rivers, okay, so this is the, if this is the water surface, okay, so in this case, the water surface gives the hydraulic grade line, okay, because that is the head, okay, although the top is zero because of the static pressure is zero because of atmospheric pressure, but you have the elevation head, okay. So this is the hydraulic grade line, and then the energy grade line is a distance above the hydraulic grade line because of the uh, velocity head, okay. Okay, so it's a distance v squared over 2g above the free surface, okay. So this is the energy grade line. This is for open channel, okay. The HGL, it coincides with the liquid surface, okay. Now, height of the EGL decreases in the flow direction unless a pump is present. So the energy gradient always decreases in the flow direction, as well as the HGL, they always decrease in the flow direction, except for idealized Bernoulli flow. For Bernoulli flow, it is horizontal, isn't it? But for actual flow, in real flow, it is decreasing in the flow direction unless a pump is present. When you have, let's say, a pump, that is when it will increase it. Okay, it will increase the energy grade line. Or when you have a turbine, it will decrease it further. Suddenly, there will be an abrupt reduction. And when a pipe discharges into the atmosphere, the HGL is coincident with the system because the pressure head is zero. You see here, it is discharging into the atmosphere, and here there's atmospheric pressure active, okay. So the atmospheric pressure, it makes the pressure head to be zero, okay. So in this case, the HGL is coincident with the system, okay. So here the hydraulic grade line will just be, you know, if we will just be within the, you know, the center line of the flow, okay. And there will be the difference, you know, the velocity head will increase, okay, increases because the diameter of conduit decreases, v increase. When v increase, because at this point the velocity increase, okay, and that's why the difference between HGL and EGL has increased, okay. And when a flow passage changes diameter, the distance between the EGL and HGL will change because velocity changes. In addition, the slope on the EGL will change because the head loss per unit length will be larger in the conduit with the larger velocity. What are we saying? When you see the pipe diameter changes here, okay, the velocity, let's say V1, V2, V2 is greater than V1. And that is why at this point you can see this is the velocity head, but here it increases because the velocity has increased, okay. Okay, so larger velocity head because smaller pipe, okay, and steeper energy grade line and hydraulic grade line because the head loss is more, because the higher the velocity, the higher the head loss, okay. And the head loss, you know, is a function of the energy grade line, because the energy grade line SF is the head loss per unit length, okay. So if this increases, it means the slope, which is SF, will also increase. So that's why it is steeper, okay. It will increase by becoming steeper, okay. So This is milder, okay, but this is steep, okay. When you take, let's say, the slope, okay, the slope here, is smaller than the slope here, and the slope represents the energy grade line, okay. And here, when they enter, they will become the same at the surface, okay, because the velocity becomes zero, hence there will be no velocity head, okay. Now, if the hydraulic grade line falls below the pipe, like in this case, you have this pipe, you can see the hydraulic grade line is falling below the pipe. So you have negative pressure head, okay? There's negative pressure head, okay? And by negative pressure head, it means the pressure, it is below atmospheric, okay? Because we are always using the gauge pressure, okay, which is reference to the atmospheric pressure. So the negative pressure, it means, vacuum pressure, which is below atmospheric pressure. Remember chapter 3, okay? So how to overcome negative pressure? Negative pressure is simply the gauge pressure is negative, or we can just call it vacuum pressure, okay? And how do we overcome it? We overcome the negative pressure by using a pump. When we have a pump, because the pump, when we install a pump here, okay, it will increase it will increase the pressure head, okay. It will increase the pressure head so that it will be above the pipe, okay. And this is another one which shows, you can see it at the entrance, here is the same EGL and HGL, but then it decreases, because of the entrance. The velocity head increases here because of the flow velocity. At this point, let me call V1, let me call V2 here, because V2 is less than V1, okay. That is why at this point the velocity head decreases, because the velocity has decreased, okay. And then it remains almost the same, okay. You can see that, but there is always loss. It is losing head. There's always head loss. And here again, you can see, because the velocity here is higher, so the slope of the energy grid line is steeper than the slope here, because V2, the velocity at section 2, is less than the velocity at section 1, okay. It is less than the velocity at section 1, and that is why the energy gradient is steeper here, because the velocity is higher, hence the head loss is higher here also. The head loss is also higher in this case, okay, because the head loss is a function of also the velocity head. And energy gradient cannot increase in the flow direction unless energy is supplied to the fluid. That is, unless, let's say, you have a pump. Let's say you install a pump here, so it will push the energy grade line and the hydraulic grade line, okay, when you have a pump. Otherwise, it does not increase in the flow direction. And if it doesn't, but the hydraulic grade line can rise or fall in the flow direction, okay, depending, but it cannot go beyond the energy grade line, okay. You can see here, because the pressure in the pipeline increases and decreases depending on the velocity. The pressure head here compared to the pressure head here, you can see here the velocity is V2 here is lower than V1. So the pressure head will increase slightly because of the decrease in velocity. Okay, remember that the physimetric height plus the velocity head is a constant. So when the velocity decreases, the pressure head, the piezometric head will increase. Okay, so that is why here it slightly increased. Okay, and then continue to decrease in the flow direction. So the hydraulic grade line can increase or decrease in the flow direction depending on the velocity, but the energy grade line, even when the velocity increase or decrease, it will only affect the slope of the energy grade line. For higher velocity, the slope is steeper than for lower velocity, but it does not increase in the flow direction unless you have a pump. That is the only condition when the energy grade line will increase. okay, unless you have a pump, okay. But the hydraulic grade line can increase or decrease depending on the velocity, in the direction of flow. If the velocity decreases in the direction of flow, then the pressure head will increase. If the velocity increase in the direction of flow, then the pressure head will decrease. I hope it is clear. And here in both cases, you have a piezometer and a pitot tube. Piezometer showing the height of the pressure head in the pipe or the piezometric head, and the pitot tube showing the total energy, which is the stagnation energy, or the height, the total head, including the velocity head. Okay, so you can see that. You can see them. Okay. Now let's take a simple example here before we take our quiz on how to draw the energy grade line and hydraulic grade line in a pipe system. Okay, so sketching the energy grade line and hydraulic grade line for a piping system. Okay, so here you have a pump. Here there's a pump that draws water from a reservoir where the water surface elevation is 520 feet. Okay, so Z1 is 520 feet, and forces the water through a pipe which is 5,000 feet long and 1 feet diameter. And this pipe discharges water into a reservoir with elevation of 620 feet. Okay, so the difference in elevation 100. Okay, so the pump is raising water through a height of 100 feet, which is 30 meters. The rate of flow is 7.85, and the head loss in the pipe is given by this. That's the Westbach equation. Okay, so we want to determine the head supplied by the pump, okay, and the power supplied to the flow. Okay, the head supplied by the pump and the power supplied to the flow, and draw the HGL and EGL for the system. Assume that the pipe is horizontal and is 510 feet in elevation. So we need to find HP. So we simply apply the energy equation. Okay, you simply apply the energy equation, which is this, to find the head due to the pump, okay, which is this one. We don't have a turbine, so this is 0. Okay, and the head loss, we were given the equation to find the head loss. Okay, because he said this is a reservoir, another reservoir, so the pressure in both cases 0 because it's atmospheric at the top, and then the velocity 0. Okay, so we have the head of the pump to be equal to the difference in elevation plus the head loss. Okay, so the head supplied by the pump provides energy to lift the fluid to a higher elevation and to overcome the head loss. Okay, so this is the interpretation. Okay, and in this case we find V. Okay, the velocity, because we have the flow rate and the pipe details. Okay, so this is the velocity, and then we can find the head loss. Now we know the diameter and the length and the velocity, so this is the head loss, and then we can find the head loss supplied by the pump, which is 178. Okay, and to find the power, we just substitute the power, the pump head here, and get the power. Here is converted to horsepower. Okay, 159 horsepower. So how do we now sketch? How do we now sketch the energy grade line and hydraulic grade line? Yeah. Here we have the energy grade line. Okay, and then from the pump provides a head of 178. Okay, so it will push the energy grade line up by 178. Okay, and then it keeps on reducing up to when it enters the reservoir. Okay, so this is simply the sketch. And what is the velocity head? We can determine the velocity head by plugging in the value of the velocity, okay, here, and this is just 1.6 feet, and that gives us the difference between the EGL and HGL, okay, which will remain largely constant because the velocity could be assumed to be uniform throughout. Okay, so that gives the difference between the EGL and HGL, which is the velocity head. Okay, any question? Because it's time for the quiz now, and this is the end of chapter 7. Next week we will take chapter 10, flow in conduits, that is pipe flow. Okay. Oh, now I have 15. So meaning two guys joined late. I told you joining late is not allowed. Joining late is not allowed. When you join 5 minutes into the lecture, you will be marked as absent. Okay? Please do not be joining the class late. Okay? Because when I started, up to when I went for break after, during the halftime, I had only 13. Okay? So I will post the quiz now on the blackboard. Do it in 50 minutes and send it to my WhatsApp number. And you remember I told you there will be 5% for grade verification. So what I decided to test you, on the whether you did the homeworks yourself or you just copied, and the quizzes as well. So on week 15 we will just agree on a time. You come here and I will pick any question from the quiz or homework. Okay, any question from the quiz, or one question from the quiz, one question from the homework, exactly, and then you solve it. Because if you solve it, it means you did not just copy, but you know what you are doing, and that one will be 5%. Okay, 5%. Okay, the aim here is to make sure you master you know exactly, the homeworks that you submitted. You didn't just copy from someone, but you can actually do it, as well as the quizzes, because all our quizzes are online. Some of you are just copying. The quiz I gave you, the last quiz, I think quiz 4 before the major, I repeated it in the exam. In the quiz, all of you got 10 over 10, but in the exam, most of you failed it. And it was the same thing, and that was because you just copied.
Doctor, not because we are copied, because you have put the wrong answer. So when we solve it and we
No,
put
no, 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 no. It's
answer,
not because
listen
it's
to me,
not
Doctor.
because it's not
Listen to
because
me.
I put
Okay,
wrong
listen
answer.
to me, Doctor.
Wait, 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 wait. The answer was not in the step, was in the calculator. So you did not memorize.
I know,
You did
Doctor.
not
مش تو listen
wait,
to me.
wait, wait, wait. I explained that. I explained this to you. You did not memorize the answer. You understand the steps. All the steps in the solution were correct. So you did not memorize the answer and just go and put, instead of 10 to the power of 6, you put 10 to the power of 8. That is not the case. So my solution has no bearing with your solution in the major. And even
Okay,
if
Doctor, what I mean.
let's assume
What?
you gave me the one that I gave you in the something, that won't make you fail it. At least you should get 90% of that question, but most of you failed it. So don't try to hide under the fact that there was a mistake in the numerical value, not the step.
You
All
are
the
not
steps were
listening,
correct.
Doctor, and you don't just response what I said. What I said is we already did it correct, but when we see as the answer in calculator not the same the answer you vote, so we are confusing. So we change everything to make it just similar to
No, no,
your
no, no,
answer.
no. No, 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 but but that is not how numerical problems are solved. I mean, nobody will ask you to memorize any answer. So, did you memorize all the answers? Did you
No,
memorize
doctor, but when you
all
see
the
when you
numbers?
see your doctor puts an answer, and when you got another answer in the exam, of course you will change it. You will change everything just to get an answer close to what the doctor put in his key
Okay.
answer.
If you
This
if
is
you change the
why we
numerical,
didn't make it well, and you can see most of students
no, no, no,
didn't
no.
get it well.
Wait, wait. Look, some of you did not even sketch it. Some of you did not even write anything. I have all of them, all of them. Some of you did not even write anything
How
to
many
even
percent of them and how many percent students vote anything just to take get a close
You may
answer
have
to your
that
answer?
problem. Wait, if you have that problem, you cannot generalize for all. If you feel you have that problem, you want to come and check your script and check that question, you are free to do that. Come and check it. Come and check it. But you cannot say that all of you are having the same issue. That cannot be an excuse. That cannot be. That cannot be. Because nobody asked you to memorize any numerical answer. I give you all the formula, I give you all the constants. So you cannot say that you have to memorize all the numerical answers to problems. That is not possible. The most important thing is to understand the concepts, and that is the most important thing. Plugging in values and getting it or not getting it, this is something different, entirely different. But when your steps are completely wrong, then there's nothing that one can do. Even if you, by any means, you try to manufacture the answer that you remember, the numerical value, you will still not get it, because the steps are the most important things. So, like I was saying, the 5%, this is a chance for you to prove that you have really solved your homeworks, you have understood all your quizzes. It will just be one question from the quiz and one from arbitrarily selected from the homework. So, if you really master it, it will be the same thing. There will be no change in anything. But we just want to ensure that you are able to solve all these problems. That is just it. So just one, and then you get your 5%, full points, full points, full points. So this is chance for you, most especially those of you that didn't do well in the exams and what have you. So you have the ability to get 5% in one sitting, and your 5% is assured. So we will try to find time during week 15, but you can start to review all your homeworks, all your quizzes. This will be the last quiz, okay? This is going to be the last quiz. And then the one that we are going to present for the assessment verification, like I said, all you need to do is to study all your quizzes and your homeworks. And the solutions are all there to make sure you can solve each one of them from the beginning to the end. Because the question is definitely going to be one from the homework and one from the quiz, and that's it. So if you are able to reproduce the same thing to solve it till the end 100%, you get your 5 points, which is a very easy way to like boost up your grade.
Excuse me. I think, Doctor, it's not a bad idea. I agree, but all of our homeworks, I think it's a lot.
Yeah, it's all the homework. It's all the homework that you are going to study. But I am not going to like test you to pick question from all the homeworks. I will just randomly select just one question. I will
Yeah,
just select
I know,
one
but
question.
excuse me, Doctor. If anyone copy something, that
Yeah,
will be appear on his marks on majors because it's uh,
I
written
agree
in
with you.
front of you.
I agree with you. I agree with you. And that is why we want to ensure that even if you copy, you have to ensure that you know what you copy. Because if you still come and take, this, if you can't solve it, it means you did not know. You can get 100% in the quiz, 100% in the homework. But if you cannot solve a question picked from the quiz or homework, then that tells us that you cannot defend the grades you got in the homework and the quiz.
That's fine. I'm agree with the idea, but all the homework it's a lot. What about uh, mm, taking the part for the finals? Because
No,
it will be like preparation and
that will
proving.
help you. Wait, that will help you to like review even for the final exam. So it will be like indirectly making you study for the final exams. Because if you study all the homeworks and quizzes, it means you are pretty well ready for the final exams. And of course, even the final exams, the questions will not be, so different from those in the slides, quizzes, and homework. So you have like indirect, it will like make you indirectly prepare for the final exams. And if you really solve these problems, then it won't take you any time to just go through them over again. But if you don't solve them, if you just copy, then that is when it will become really, a headache for you to like master all the solutions. But if you really solve them from the beginning, understood every concept, then it won't take you any time to prepare for this.
I agree, but I'm still thinking about it's a lot to prepare because we don't
No,
just study
yeah,
food, study a lot of courses, so
no,
we have to
but
prepare for many of them.
but but these are things that you solved yourself. If you solve yourself, it will take you just a few minutes to go over the solution.
Of course,
And
I
that's
know,
it.
but about the quiz and homeworks, you can't memorize the steps exactly
No, it's
for
not
each
memorized.
one.
It's not memorized, but understand. If you really understand them when you submit it, it means now you can just like it will just take you a few minutes to go over them. But if you did not understand them at that time, then that is when it will give you a headache. I have already posted the quiz
It's
on
already
the
on Blackboard.
yes, I already posted it.
Yes, I see it. Thank you, doctor.
All right, you're welcome.